Have you ever wondered how electrical quantities like current, voltage, frequency, power, and energy are measured? This is not just a question for electrical engineers, but for anyone who has ever been curious about the invisible forces that power our world. Today we're going to delve into the fascinating world of electrical quantities, beginning with current. Imagine a river flowing with water. Just as the water flows from one point to another, electric charge flows in a circuit. This flow of electric charge is what we call current. It's an integral part of any electrical system, from the tiny circuits in your smartphone to the vast power grids that supply electricity to entire cities. And just like the flow rate of a river is measured in liters per second, the flow of electric charge or current is measured in amperes, often shortened to amps. But how do we measure this invisible flow of electric charge? Enter the ammeter, a crucial tool in the world of electronics. An ammeter is a device that measures the current in a circuit, but there's a catch. Unlike a ruler that you can simply hold against an object to measure its length, an ammeter needs to become a part of the circuit itself. It needs to be connected in series with the circuit. Think of it as a toll booth on a highway. All the cars, or in our case, the electric charges, have to pass through the toll booth, or the ammeter, for us to count them. The reading on the ammeter tells us the amount of current flowing through the circuit, just like a toll booth operator can tell us the number of cars that have passed through. So, in a nutshell, current is the flow of electric charge in a circuit, and it's measured in amps. And to measure this current, we use an ammeter which needs to be connected in series with the circuit. So an ammeter allows us to measure the amount of current flowing through a circuit. This is just the beginning. Stay tuned as we explore more about the intriguing world of electrical quantities. Following current, the next crucial electrical quantity is voltage. Think of voltage as the driving force behind the electric current in a circuit. It's the push that gets the electrons moving. Without voltage, there would be no current, no flow of electricity. To put it in more precise terms, voltage, or electric potential difference as it's sometimes called, is the energy per unit charge that a device can provide or consume. It's the amount of oomph behind each electron as it moves around the circuit. This is the force that drives the electric current, and it's measured in units called volts. Voltage is a fundamental concept in the world of electricity and electronics. It's what makes your light bulbs glow, your fridge cool, and your phone charge. It's the difference in electrical potential between 2 points in a circuit that causes the current to flow. Now, how do we measure this force that's so vital to our daily lives? We use a device called a voltmeter. A voltmeter is a tool that measures the voltage or potential difference between 2 points in an electrical circuit. It's like a ruler for electricity, but instead of measuring length or distance, it measures force or potential difference. The voltmeter works by connecting in parallel across the component or points where you want to measure the potential difference. This means it's hooked up alongside the part of the circuit you're interested in, not in series with it. This is important because it allows the voltmeter to measure the voltage without significantly altering the current in the circuit. But remember, a voltmeter doesn't generate voltage, it only measures it. It's like a speedometer in a car. It tells you how fast you're going, but it doesn't make the car move. In the same way, a voltmeter measures the force that pushes the current through the circuit. It gives us a way to quantify that force, to understand it, and to use it to our advantage in designing and managing electrical systems. Moving on, let's talk about frequency. Frequency is a term that you may have heard in various contexts, but in the realm of electrical engineering, it has a specific meaning. It refers to the number of cycles per second in an alternating current or AC signal. This concept is crucial in understanding the behavior and characteristics of AC circuits, which are ubiquitous in our daily lives. Let's delve a little deeper into what a cycle means. In an alternating current, the current oscillates or alternates between positive and negative values. This oscillation forms a wave-like pattern, and one complete wave, from peak to peak or trough to trough, is what we refer to as a cycle. Now, how do we measure the number of these cycles occurring every second? The answer is, quite fittingly, in Hertz. Named after the German physicist Heinrich Hertz, Hertz is the unit of frequency. 1 Hertz represents 1 cycle per second. So when we say an AC signal has a frequency of 50 Hertz, It means that the current is completing 50 cycles of oscillation every second. But how do we determine this frequency in real-world applications? Well, we use a device called a frequency counter. A frequency counter measures the number of cycles of an AC signal that occur in a specific time interval. It counts the number of times the signal crosses a certain voltage level in a given period, and from this, it calculates the frequency. Alternatively, frequency can also be determined by observing the number of cycles in a given time interval on an oscilloscope screen. This method, however, requires more manual calculations and is less precise than using a frequency counter. In a nutshell, frequency is the measure of how rapidly an AC signal oscillates, and it's measured in hertz. Understanding and measuring frequency is key to managing and optimizing AC circuits, from the power supply in your home to complex industrial machinery. Thus, frequency counters help us measure the rate at which current oscillates in an AC circuit. Next up is power. Power, in the realm of electricity, isn't about dominance or control. Rather, it's about the rate at which energy is transferred or converted. Just like a sprinter who uses their energy to move as quickly as possible, electrical power is all about how swiftly energy moves from one point to another. In technical terms, power is quantified in units called watts, a term you've probably heard when talking about light bulbs or your microwave's output. To grasp power, we need to understand its relationship with two key electrical quantities we've already discussed: voltage and current. Think of a water pipe. The voltage is the water pressure, and the current is the flow of water. The power is then the overall work done to move that water. In an electrical circuit, power is the work done to move electric charges under the influence of an electric field. The formula for power is quite straightforward. It's represented by the symbol P, and it's calculated as P equals V times 1, where V stands for voltage and I is the current. So, in essence, power is the product of voltage and current. If you increase the voltage or the current, the power will also increase, and vice versa. While this formula offers a convenient way to calculate power, sometimes we may need to measure it directly. This is where a wattmeter comes into play. A wattmeter, like the name suggests, measures power in watts. It's a handy device often used in various applications, from testing the power output of a new gadget to checking the power consumption of an entire building. But remember, power is just a snapshot. It's the rate at which energy moves at a specific moment. It doesn't tell you how much total energy is used over time. That's a different story, and it's related to another crucial electrical quantity we will discuss next: energy. So, by measuring voltage and current, we can also calculate the power in a circuit. And with that, we've unlocked another piece of the electrical puzzle. But don't rush off just yet. There's still more to explore. Stay tuned. Last but not least, we have energy. Now, energy is a term that's thrown around quite a bit. But what does it really mean in the context of electricity? Simply put, energy is the total amount of work done or potential to do work. It's measured in watt-hours or joules. Let's break it down. A watt-hour is the amount of energy consumed when 1 watt of power is used for 1 hour. Think of it like this. If you turned on a 1-watt light bulb and left it on for an hour, it would consume 1 watt-hour of energy. On the other hand, a joule is a smaller unit of energy, and it's equivalent to the energy transferred when 1 watt of power is used for 1 second. But how do we calculate energy? Well, energy is calculated by multiplying power by time. So if you know how much power a device uses and for how long it was on, you can calculate the energy it consumed. For example, if a light bulb uses 50 watts of power and it's on for 2 hours, it would consume 100 watt-hours of energy. That's 50 watts times 2 hours. Now you might be thinking, that's great, but how do I measure energy? Well, that's where energy meters come into play. These devices are commonly used to measure electrical energy consumption. They measure the amount of electrical energy consumed over time, and you've probably seen one in your own home, the electricity meter. It's that box on the side of your house that the utility company reads to determine your electricity bill. In conclusion, measuring electrical quantities is essential to understanding and managing electrical systems. Each quantity, current, voltage, frequency, power, and energy, has its own significance and method of measurement. They all work together to create the electrical systems that power our world, from the smallest circuits in our gadgets to the largest power grids that light up our cities.